My name is Ali Azam, and in this course, we are going to be looking at privacy techniques used in different blockchains. But before we go into that, I want to look at why this course. So, first of all, we have to answer the question, how does anyone learn about privacy today? And the answer is everyone has to search on Google, ask friends, ask other software engineers, and read lots of papers, and it takes quite a lot of time. And the biggest problem of that is because there is no single resource for learning all about privacy. And this is the gap I want to fill. You want to think about hash functions, Merkle trees, ring signatures. Everyone should know about them. Even if you don't use them that often, you should know how they work and when to use them and when not to use them. So everyone can take advantage of these cryptographic techniques. And so, who is this course for? Well, for anyone who wants to learn about privacy on blockchains, we are going to deep dive into them. We're going to understand different protocols. We're going to analyze them. And we're going to build really cool applications like rock, paper, scissors, and a few more. So, this is a very hands on course. We are also going to talk about the theory, but we're also going to implement that theory and test it out. If you want to build decentralized applications, this is the course for you. If you want to solve puzzles, we are going to have some interesting puzzles, and that's all going to be about privacy. So what will you actually do in this course? This is a very short course. So first of all, we're going to look at the intro to privacy on blockchain, and we're going to see what is a blockchain, what is mining in blockchain, what is privacy, will quantum computing break privacy, and we're going to look at the privacy techniques used in different blockchains like ZCash, Monero, Dash, stealth addresses, Coinjoin payment channels, etc. Zero knowledge proofs, of course, and a few other things. And the second module, we will look at implementing rock, paper, scissors game on Ethereum, and we will do it in an iterative fashion. And I will give out tasks, and you can do it yourself first, and we'll go through it together. So if that sounds interesting, stay tuned, and I have a lot more of this. Hello and welcome to the Module 1 of Intro to Privacy and Blockchains. In this lesson, we're just going to explore what we are going to go through in this module. So first of all, we are going to look at intro and just getting started. So just having your environment set up and just walking you through a bit of basics. So then we are going to start with what is a blockchain, and how does it work in overall brief principle. Secondly, we're going to go through what is mining in blockchain, what is privacy in blockchain, and we're also going to explore some interesting concepts around quantum computing, because that's always a threat, because most of the things rely on cryptography, and there's certain types of cryptography which quantum computing can break, and we'll look at how we can already do things like post quantum cryptography, and how we can already use algorithms which are quantum safe. So after that, we are going to go into a bit of a dive into the current privacy blockchains that are out there, such as Zcash, Monero, Dash, and there are some mixes for Ethereum. There is something called one-time addresses and stealth addresses, and we are going to deep dive into all of them. So stay tuned, and we'll just dive right in. Privacy is a very important concept in blockchains. Writing smart contract is one thing, but designing the privacy aspects of your application is another. Using cryptography as a toolbox can be a way to achieve privacy that can yield very good results. For example, hashes with salt have been used for a long time to store user passwords without actually knowing the user passwords. And even if the security gets compromised and they are stolen, no user data can be accessed by using the hash without knowing the pre-image of the hash. This essentially means that if a website gets hacked, and the user used the same password across multiple websites, the hacker does never finds out about the password itself, so they can't go and hack their other accounts. And this is much safer than storing this password in plain text. Privacy is at the heart of blockchains. Blockchains such as Bitcoin and Ethereum are very public by nature. To use them for your applications, you must not put any sensitive data on them because everything will be public. But you have to put something so at a later date, so you can prove that a supply chain holds or a product is legitimate. But how do you go about putting data on blockchains without really revealing what the data is? There are many solutions to that problem. For example, a most commonly used one is hashing. A hash function is a deterministic function which takes a pre-image and returns a hash, such as the one shown below. There are many functions such as kekek256, SHA-3, SHA-256, SHA-2, SHA-1, and so many more. This essentially lets us put the hash on chain without revealing the pre-image. Anyone who has the pre-image can verify on their local machine that it's valid. Well, what if we have many pre-images? They can all be hashed together, like the second line we've shown here. They can just be all written one after the other, and the order is important. If you change the order of the way you put in the hash function, then the hash will change. And the hash function gives a guarantee that if you give the same pre-image, it will always result in the same hash. So if someone's password is ALI and you hash that, then the next time you hash ALI, it's going to be the exact same thing. But if you do not synthesize your inputs, then it will likely change. This works fairly well, but there are better ways to do this, such as a Merkle tree. In a Merkle tree, you only have to reveal the relevant parts of the tree, and the tree is formed of hashes. So even when you reveal certain branches, you're only revealing hashes and not the pre-images. Now that you may think that's all great, but you don't want to reveal anything but prove that you know a secret. This is the fascinating world of zero-knowledge proofs. There are many variants of zero-knowledge proofs, but there are mainly two branches: interactive zero-knowledge proofs and non-interactive zero-knowledge proofs. In this course, we will deep dive into different ways we can achieve privacy without knowing anything about the mathematics behind the cryptography and evaluating the tools within the cryptography toolset. Even more, developing a mindset for building privacy-preserving applications which are simple, scalable, and can be adopted for both Web 2 and Web 3 applications. Furthermore, we will develop blockchain-based privacy applications such as implementing rock, paper, scissors on Ethereum with complete privacy for user moves, and developing more interesting ideas using linkable ring signatures, Merkle trees, ZK snarks, and many, many more. Okay, so what is a blockchain? We're going to look at the definition from Wikipedia. It says, a blockchain, originally blockchain, is a growing list of records called blocks that are linked together using cryptography. Each block contains a cryptographic hash of the previous block, a timestamp, and transaction data, generally represented as a Merkle tree. Now, that's a lot going on in there, so we're going to try to break it up. And let's see what components are there in the blockchain. So first of all, a blockchain differs from normal websites or normal databases that it has a peer-to-peer network. A peer-to-peer network is formed between peers who have equal privileges and share all the data between each other using a gossip protocol. In this kind of network, every node can talk to every other node, and nodes can drop out and new nodes can join in without any authorization. The second component of blockchain is consensus mechanism. Having the peer-to-peer network is great, but without having a centralized server, how do these nodes come to an agreement? That is the question. The answer is consensus mechanism. A consensus mechanism is a way by which these nodes can reach an agreement. Consensus mechanisms have existed before the era of blockchains and have been widely used in distributed systems, such as Paxos and Raft. Bitcoin used a new consensus mechanism called proof of work. The idea was simple. If you can prove that you have done some computation before anyone else, you will be rewarded, and the consensus is achieved by validating the computation. We will talk about this more in the next lesson. The third component is the most important one as well, which is cryptography. Without it, the blockchain could not exist. Blockchain relies heavily on cryptography, such as hashes, Merkle trees, digital signatures, public key cryptography, and more. We'll walk through each of these in the cryptography module. There is a lot more that the blockchain has to offer, but to understand and improve privacy, for blockchain-based applications, we must deep dive into the fundamentals and understand the limitations of blockchain from privacy perspective, and we'll be looking into several blockchains and analyzing their privacy. This should give you a general idea of what a blockchain is, but we're going to deep dive into the mining which creates blocks and how that works. So stay tuned. Okay, so in this lesson, we're going to look at a little bit more about the blockchain structure and how the blocks are linked. So first of all, we have the green block, which is called the Genesis block. It's the first block that is created, and every block after that has to reference this. So it is an ancestor of all blocks. So it's the first block that ever gets created. It's been there in Bitcoin, Ethereum, and every other blockchain. The Genesis block is where you know which chain you're pointing to. So when you have the Genesis block, that's where the blockchain begins, and then you can start mining blocks after that. In the Genesis block, you can define any arbitrary amount. So if I was to create a new blockchain today, and I could assign an address any amount that I would like, and that's perfectly fine. So anyone who joins this chain after that agrees to the rules that are set within the Genesis block. And if they don't follow the rules, then their blocks and transactions will not be accepted. So after the Genesis block, more blocks can be created, and as you can see, the black block gets created. And after that, there's basically two miners or two miners who create the same block, but they do it at the same time. So how do we decide at this point in time which block is the one that we're going to accept? Well, this is the case that we don't actually accept this. And what happens is that the miners then start another race and say, if I can create the next block and point it to my block rather than the other one, then I can get the reward for both. But if no one follows this block and it's just abandoned, it's called an orphan block, because the main chain is the longest chain, or is the chain with the most proof of work. So if it happens to be the case that two miners created a block at the same time, then the main chain is the chain with the most proof of work. And at this point in time, when there is two blocks, the proof of work is the same. So what happens is that you'd have to go, the miners actually start another race, and they say they are going to now create the next block. And if whoever wins that race will then go further. And you can see this happening again at this point in time, where the black one and the purple one again gets created at the same time. Well, that's fine, but this is what we call a fork. But it's only a fork if if there's quite a few blocks after that, and people actually follow it, and it remains alive. But most of these forks, which are abandoned or orphan blocks, eventually die out. So in this case, you can see that when the purple block gets created, again after two blocks, the black block gets followed the most, and it has the most proof of work, and then it further divides up. Because Bitcoin blocks are 10 minutes every block, that's why these can actually happen quite a lot. That of quite a few miners create a block at the same time. They may not have necessarily the same transactions, but then one of them will be orphaned and the other will carry on. However, in Ethereum, there is this concept of uncle blocks, and uncle blocks actually mean that instead of throwing them away, they actually accept them, but they pay a lower reward. So miners, when they mine, they get a reward, and that's what we're going to talk about in the next lesson. Okay, so let's talk about what are miners. So far, we've talked about the consensus mechanism and a little bit about proof of work. Now, let's see how everything fits together through mining. So, in a distributed peer to peer network, everyone has the same privileges. So, how do we ever confirm that the transaction is indeed now confirmed? For example, let's say Alice sends some currency like Bitcoin to Bob. How does Bob know that Alice hasn't also sent this to Charlie? This is known as a double spending problem. Since there isn't a central party like a bank to keep track of transactions and accounts, people can double spend what they have, and this is the problem that Bitcoin solves in a distributed way. The idea is very simple. Everyone is considered equal, and there are special type of nodes which are known as miners. The job of a miner is to create blocks and confirm transactions. Miner is incentivized to do this in mainly two ways: block rewards and transaction fees. Block rewards are the main way miners make money. In Bitcoin's case, this is hard coded in the protocol and are halved every 4 years, roughly. And transaction fees is the second way miners make money. Every transaction has a fees associated with it that goes to the miner who includes this transaction in the block. Blocks have limited space, so they can be propagated faster to all the peers in the network. The miner is incentivized to only include transactions which pay them the highest amount of fees. This means that transactions with zero fees can still get confirmed, but transactions with higher fees will always be picked up first by a rational miner. Now, let's talk about what a miner actually does. Mining, yes, that's correct, but there is more to it. Essentially, they are solving mathematical puzzle. For example, if I ask you to find two prime numbers which multiply to get 15. Now, finding these numbers is harder than verifying them. Since 15 is a small number, we can say that 3 and 5. But it's much simpler to multiply 3 and 5 to get 15 than to find two prime numbers which multiply to get 15. This is the difficulty in Bitcoin. The higher the prime number, the harder it is to find, and therefore the difficulty is higher. And this is how Bitcoin maintains a block time of 10 minutes. If the miners solve the puzzle too fast, the difficulty will get increased, so the number will get higher. If the difficulty is too high, it will take longer time. And if for consistent times it takes longer than 10 minutes, the difficulty will be reduced. So essentially stabilizing the time to be roughly 10 minutes. In Ethereum, this is currently around 15 seconds. We will talk more about this in the coming modules. What is privacy within blockchain? Now that we know what is a blockchain and how blocks are created, we can now deep dive into the privacy that's within blockchains. So, how would you feel if all your bank transactions were made public? Everyone in the world can now see how much you spend on coffee and how much your rent is, and basically all your financial data is now public. This is more or less what Bitcoin does, with one key difference. The account is identified by a 42-letter hexadecimal instead of your name or account number. And we'll take a look at this in a second. You can of course spread the money in as many accounts as you would like, but remember that they are linked and everyone in the world can say with good probability that it's owned by you and there isn't really much privacy to begin with. There are multiple ways you can hide your privacy with open networks like Bitcoin and Ethereum. And there are many privacy focused cryptocurrencies that we will dive into within the advanced course. For example, let's take a look at ZCash. It allows the users to stay completely open just like Bitcoin, or users can hide their transactions by entering the shielded pool. The shielded pool uses ZK snarks, zero knowledge, non interactive arguments of knowledge, or in other words, fancy cryptography to hide the amount, the sender, and the receiver. And any observer of the network does not find out anything. Only the receiver knows that he received the money. The miner can validate a zero knowledge proof, which proves that the sender has the money that they are spending, so that prevents double spending, but finds absolutely no information about the sender or the receiver. Similarly, Monero uses ring signatures and confidential transactions to achieve privacy. We will talk about all these techniques later in the course and how you can use them to your advantage. So this is a Bitcoin block explorer, and in here you can find out everything about the block, the transactions, the hash rate, and the basically who was the miner, the size of the block, and everything else. So let's start by looking at the latest block. And in the latest block, you can see, first of all, the hash of the block, which is unique to the block, the confirmation. So that's basically the height that's currently being built after this block. So this is the confirmations that are used when you buy something. So if you go and buy something expensive or sometimes even coffee, they will say that they will wait for 6 confirmations. That means there will be 6 blocks after this, and then they will accept that the transaction actually happened. So this is what we call a probabilistic finality. At any given point in time, we only have a probability that the transaction will not be reverted. So when there is only one confirmation, the probability that the transaction will not be reverted or the block will actually get orphaned is very high, which is why the recommended confirmations for Bitcoin is 6 or even 18 if it's a very high value transaction. So of course there was a timestamp, there was the height, there is the miner. For this one is unknown. It's just an address. We don't know who this is, but we can look at other blocks where this is known. And the things that we can actually look at are, for example, the fee reward and the block reward. This is what the miner gets for mining this block. So they earned 6.25 BTC, which is the current amount that miner gets for mining a block, and in transaction fees they receive 0.177. And we can also go down further and start looking at the block transactions. So you can look at each individual transaction and see what's happening, and you can also see that there's confirmations, so you can go down. But this is basically what the block explorer is. We can go back and start looking at a miner like F2 pool, and so miners are actually known and they also work in pools. So if you have some computing power, you can become a part of a pool and you get a fraction of this mining reward. And so they can confirm transactions, and you can see this is the amount of BTC that they have received over time. And you can again see different transactions. You can see that the Coinbase newly generated coins and a lot of other things, and you can go down into what the transaction does itself, and it will basically tell you what the inputs and the outputs are. So because Bitcoin is a UTXO based model, and Ethereum is an account based model, they both have their advantages and disadvantages, but it's out of scope for us to go too deep into that. but there is some really great resources out there if you would like to learn more. But you can go and explore around what these block explorers show you. You can trace different addresses. You can see how many transactions they have, how much BTC they own, and what their current balance is. You can of course send and receive as well, so you can, for example, see how much money is owned by a single address. And this is again just a public private key pair which owns this. And of course, if someone could guess the private key correctly, they can get all this money. But it's almost impossible. Okay, so let's try to see, why is privacy important? Well, first of all, because all of these blockchains are public, we're now looking at Etherscan, which is a block explorer for Ethereum. Because they're all public, you can go into any account and look into how much they own and what their transactions are. So, for example, we can go into this account and see that it made a transaction 38 minutes ago, then it made one 28 minutes ago, and it made one a minute ago. And we can exactly see what it's doing. So, by doing any sort of analysis, you can actually find out what they're doing, what their transactions are, and where they're spending their money. And this is what a lot of companies do, like chain analysis and many others. So you can look into every account, every transaction, and know what they're doing. So it is very important to have privacy, because otherwise everything that you do is public. And for this, Ethereum and Bitcoin have many solutions that are out there, and we're going to go and look into each one of them. And this is where you have many different privacy techniques to keep you hidden in the public setting. It is important that you design your applications with privacy baked into them, so the user doesn't have to care about privacy at all. But unfortunately, most of the applications that run on Ethereum are very public by nature. For example, you could see in this one, it's talking to Uniswap version 2. And you can go into that and you can see all of the transactions that are happening, and nothing is hidden at all. So you can go and read the source code, and you can go and look at all the transactions that are happening. And pending basically means that the transaction is sent to the miner, and it's waiting to be put into a block, and waiting for confirmations. So this is very important, that when you design your applications, you take all these considerations and you try to design them with privacy in mind. So your users don't have to worry about them at all. So the question that's ever present is, will quantum computing break privacy? And to understand this concept further, we have to look into the cryptography world and understand what does exactly the quantum computing breaks. So post-quantum cryptography refers to the cryptographic algorithms that are ought to be secure against an attack by a quantum computer. As of 2020, this is not true for most popular public key algorithms, which can be efficiently broken by a sufficiently strong quantum computer. The problem with currently popular algorithms is that their security relies on one of the three hard mathematical problems: integer factorization problem, discrete logarithm problem, or the elliptic curve discrete logarithm problem. All of these problems can be easily solved on a sufficiently powerful quantum computer running Shor's algorithm. Even though current public known experimental computers lack the processing power to break any real cryptographic algorithms, many cryptographers are designing new algorithms to prepare for a time when quantum computing becomes a threat. And the systems that are in place today and are being designed with the consideration of quantum computing breaking the cryptography. So, in cases where it is possible to use a post quantum or quantum safe algorithm, it should be recommended and it should be used. And we have quite a lot of progress in this area that we can go into, and we will look more into this in the cryptography module. Okay, in this lesson, we are going to look into the privacy techniques and blockchains which exist today to provide privacy in cryptocurrencies. So one of the most famous ones is ZCash, and we're going to look into it and how it works and how it provides privacy. We're not going to go into the mathematical details, but we're just going to look at it from a fundamental level and understand the high-level design of the ZCash itself. And then we're going to look into Monero, which is another cryptocurrency which provides privacy, and also Dash, Mimblewimble, and we're going to look at how mixers operate and what privacy guarantees they provide, and also stealth addresses and one-time addresses, which are also used in Monero quite a lot, and also a version of them is available on Ethereum and some other blockchains. We're going to look at the general idea and how they work and how you can implement them yourself today. In this lesson, we are going to look at Zcash. Zcash works by building on top of Bitcoin and adding privacy by using ZK snarks. Zero knowledge, succinct, non-arguments of knowledge. In Zcash, there are two types of addresses: transparent addresses and shielded addresses. Intransparent addresses don't offer any privacy and have similar model to Bitcoin. The shielded addresses works by putting the coins in a shielded pool, and once the coins are in the shielded pool, they can be transferred with complete privacy within the shielded pool. And no one finds out any information about the funds, or where they have been transferred, who has received them, and who was the sender. So the sender, receiver, and the amount are all hidden within the shielded pool. Let's look at an example. For example, when Alice wants to send some currency to Bob in Zcash, and if she's using the transparent addresses, it's all public. So you can go and see that Alice actually sent a transaction to Bob and Bob received it. So everything is completely public. But what instead she can do is she can enter into the shielded pool. And if Bob is also in the shielded pool, then she can make a transfer within the shielded pool, which will allow her to hide her privacy. However, in reality, most of the users of Zcash actually only use transparent addresses. They are classified as Z addresses and T addresses. T for transparent and Z for shielded transactions. And once you are inside the shielded pool, you can make any transfers, and as long as you don't come out of the shielded pool by deshielding, you don't lose any privacy. And if you stay in the shielded pool always, then you have the complete privacy and no one finds out anything about your spending, and you get complete privacy for that. So Monero is another currency like Zcash which provides privacy. Monero works by using ring signatures to achieve privacy. Ring signatures don't require a trusted setup and provide reasonable privacy guarantees. Ring signatures work by introducing the concept of rings. Let's say there are 10 transactions with 10 senders and 10 receivers. What a ring signature does is create a signature such that the probability of any transaction belonging to a single sender is the same as anyone else within the ring. As you might have already thought about, the ring only works if the values are the same. Otherwise, because of the varying amounts, it can break down. But however, with ring CT, varying amounts work, and we'll talk more about this later on. The ring is composed of, first of all, the transaction that you've sent, the non-signers, the people who are not actually involved in this, and also the people who are signing the transactions, and also the outputs of the previous transactions on the Monero blockchain. And this is randomly taken so that every ring contains transactions on the Monero blockchain that were from before to increase the ring size. And the larger the ring, the higher the privacy. And you can think about this as very similar to the shielded pool, but the shielded pool works by using ZK snarks, which require a trusted setup. But Monero uses ring signatures, which don't require a trusted setup. And every ring can be different, and they provide a reasonable probabilistic guarantee of privacy. Once the ring is composed, no one knows who the sender or the receiver or the amount is. Everything is hidden within the ring. And if one of the rings of multiple blocks are broken, it only breaks that one ring, not every single ring, because there's randomness within the ring signatures and how they are used. So Monero is also similar to Zcash in terms of how it provides privacy, and it uses quite good cryptographic primitives to do that. You can read more about it in the links below, and we'll talk more about these techniques later on. In this lesson, we are going to look at Coinjoin. It's classified as one of the ways you can achieve privacy within Bitcoin. And Coinjoin is basically a trustless method for combining multiple Bitcoin payments from multiple spenders into a single transaction to make it more difficult for parties to determine which spender paid the recipient or recipients. So before we go a bit deeper into this, it's good to understand how Bitcoin transactions work. So in a Bitcoin transaction, there are certain inputs and certain outputs. You can have as many inputs and as many outputs as you want, as long as you follow this rule, which is that the sum of the outputs are actually equal to or less than the sum of the inputs. So it means that you're not trying to spend more than what you have. So in this case, it doesn't say that you cannot use multiple addresses, and you can create a transaction which has multiple inputs from different addresses and multiple outputs. So a single transaction can use any number of UTXOs, unspent transaction outputs. And this is essentially what is used to do a coin join. In a coin join, multiple senders, multiple spenders basically incorporate their inputs and outputs. So you can't actually tell which one does it all belong to one person, or does it belong to 10 people, or does it belong to how many? So it essentially hides it very efficiently. And that is the concept of a coin join. And you can read more about it on the Bitcoin wiki. But that is the basic concept, that you combine multiple inputs from different spenders and you make a single transaction in a trustless fashion. And when the transaction is executed, everyone comes out with different values, and therefore one cannot differentiate between the spenders, whether these inputs are all belonging to a single spender or they belong to different spenders. And this is the main idea about coin joins. In this lesson, we are going to look at Dash, which is a privacy-centric cryptocurrency as described in the white paper. And Dash is mainly different from Bitcoin in two ways. One is the masternode network, and it has other features such as private send. And the masternode network essentially works by people running nodes that are very powerful, and they can process transactions much faster and much quicker. And to do that, they have to stake some of their Dash, which is described in the white paper as 1,000 Dash. But we are more interested in how it provides privacy. So what we are going to look at is what is the private send. And private send is essentially an extended version of a coin join. So you can do coin joins with other people, and you can chain them together to get even more inputs within a single transaction. But the problem is that the Private send transactions are not very common in Dash. They are only 0.8% as of a study done a couple of years ago. And this is one of the problems, but it does provide reasonable privacy with Coinjoins. And you can read more about it here, but essentially it's an improved and extended version of a Coinjoin, and it essentially does mixing. And we're going to take a look at some other mixers in the next lesson. But as we've learned in the previous lesson, that Coinjoin essentially takes multiple inputs from multiple spenders and combines them into a single transaction, hiding the true identity or true identity of a single spender. And this is a very useful feature, and Dash is actually makes it much more usable and user friendly. In this lesson, we are going to look at how state channels and payment channels work and how they provide privacy. So, in a normal setting, if Alice wants to send some currency to Bob, she will send a transaction to the blockchain, which will get mined, and Bob will eventually receive the money. Now, imagine that Alice actually wants to send the money in many different transactions. So every minute, every second, she wants to give Bob like a fraction of the money instead of giving it all together or paying late. So instead, what she can do is she can use a payment channel. And how a payment channel works is by locking up funds in a contract. So what Alice will do is lock up the funds in a contract using a transaction. So let's say she locks up 10 currency, and now once the funds are locked, Bob is satisfied that he will get at least the amount that's locked in the contract. So Alice can now send signed messages to Bob, as many as there are, and she can send them directly, so it doesn't actually interact with the blockchain in any way. So first of all, it's completely private. No one ever finds out how much money did Alice send to Bob or how many times they send it. They just know that some communication must have happened outside the blockchain, and if any of the actors are malicious, the contract actually enforces that by time locks. And she can send as many signed messages to Bob, and it's up to Bob on when Bob wants to take the money out from the contract. So what Bob can do once he is satisfied and he doesn't want to wait any longer is he sends the transaction to the contract using the messages that he received, and the only thing that he needs to send is the latest message. He does not need to keep track of all the messages. He just needs to keep track of the latest message, because in every message the amount that he received gets increased, and therefore he can send a transaction to the contract and claim the funds that is his. And this is very efficient because in terms of storage, he only has to keep the latest signed message from Alice. And if Alice tries to betray him and go to the contract, he can always use the message M and show that it's actually owned to Bob, and the contract will give the money to Bob and not to Alice. So this works fairly well, and it provides very good privacy in terms that you never reveal the actual transactions, only the amount that you're taking out. But of course, it's not perfect. One-time addresses are very simple addresses which are only used once and never used again. That's all there is to it. It's very much possible in private blockchains and also in public blockchains when you can split the money in multiple accounts and only use them once. And stealth addresses allow and require the sender to create random one-time addresses for every transaction on behalf of the recipient. The recipient can publish just one address, yet have all of his/her incoming payments go to a unique address on the blockchain, where they cannot be linked to either the recipient's published address or any other transaction's address. By using stealth addresses, only the sender and the receiver can determine where a payment was sent and no one else. So stealth addresses are used by Monero quite a lot, and there is a link in the description below where you can find out more details. Hello and welcome to the module 2 of the course. In this module, we are going to build rock, paper, scissors on Ethereum. The idea of this module is to give you hands-on experience with implementing privacy-focused smart contracts on Ethereum. Ethereum is the most widely used smart contract platform, which is very easy to get started with, and we'll be writing code in Solidity. Feel free to try out Viper, which is like Python, and other smart contract languages and platforms. However, the focus here is to get the right approach and think about privacy in everything you develop, and think about the limitations. This is a lot more about the architecture and design and how to write code. The languages and platforms evolve over time, but the fundamental approaches remain the same. In this simple rock, paper, scissors application, we will deep dive into how one can play rock, paper, scissors without revealing what their move is, and letting the smart contract decide the winner in a fair way. And to make this even more interesting, you can always add incentives such as both players deposit an amount before the start of the game, and once both players have played their moves, the winner gets both the deposits. And you can extend it in many different ways. But for this module, we will look at how to implement a basic rock, paper, scissors, then we will enhance its privacy, and then we will go further. So stay tuned. In this lesson, we are going to be setting up the environment in which we are going to write the code in. And for this, we are going to be using remix.ethereum.org. And this is an online IDE which allows us to write Solidity, and it lets us also run it using an in-browser blockchain. So we can compile the contracts with different Solidity versions that you can see here. For this, we are going to be using just 0.6.0.6.1 or 0.6.0, just anything of that. And we are going to run the auto compile. We're going to enable optimization. I mean, that's really only for deployment if you want to, but we don't care about these things too much. So this is where you have the files. So when you write files, you get this contract by default to show you how it works. So this is a contract that when you open Remix, you will see this, and you can run this. So this is basically where you have the contract, and after this you can go to the compile, and you can compile the contract. It will get compiled, and you can of course see the ABI, the bytecode, and a few other things, and you can deploy and run transactions. So you can see this environment, and the environment is basically what we're going to be using JavaScript VM. It's extremely fast because it's running in your browser. It does not really have any waiting times because it's more like an emulator. So we can test our blockchain code very fast and very efficiently. It also has debuggers, which allows us to do other things, and it gives us multiple accounts. So you can see each of the accounts have 100 Ether, and you have like 10 accounts. And you can specify, of course, the gas limit, the value that you are sending to the contract, and if you were using a different environment such as injection Web3 or Web3 provider, then you can also access the deployed contracts if you have the source code. So, and you can also go and change things in settings. So you can install different modules which will help you to do different things, and you can also change the viewing. So I am now in a dark theme, but you can also change the theme within settings. So whichever one you prefer, you can customize it. But for this, we are going to be looking at just writing the code and compiling it and running it, so we can test out that our code works and It's actually deployable and runnable. But we are going to be doing it on the JavaScript VM because it's extremely fast. We're going to be using 060, or you can actually use any of these ones that you want. And this is essentially how you specify which versions that you want. We'll go through the code in a bit, but this is just to get you to set up various different things. You don't need to install anything else for now. Of course, you're free to try out anything that you want. These are just different modules that you can install, which will help you to do different things. And for now, we are just going to be starting with a plain file with this. So have a play around with this. It also comes with a terminal where you have Ethers.js installed, Web3 version 1.0, and Swarm as well. So in this case, for example, I can just show you that you can write Ethers, and then it will give you an Ethers instance. So just to show you that it actually works, you can do ethers.utils.id, which is how you hash anything, and you can just type anything in there. And of course, you would have to print it out to see the result. I mean, sometimes it does it without, but yes. So you can see this is like a hash of anything, a KK256 hash of that. So play around with this, get to know this a little bit more. And if you want to set up Visual Studio Code, you can also do that. But for this thing, we will only be looking at Remix because it's easy to deploy. If you are running Visual Studio Code, I recommend that you go and install Ganache CLI, which is also a blockchain emulator that you can run standalone. It's a blockchain that runs and mines on demand. So all the links will be in the description below. So look at that. And if you have any questions, send me a message. Okay, so let's start by creating a new file. I am going to name it game, but you can name it anything you want. The name of the file and the name of the contract do not have to match up. The only thing that matters is that you have a contract name, and that's all. So the first thing that we have to do is define the Solidity version that we're going to be writing the code in. So as I've said before, we are going to be using 060, and that's fine. So we are now going to create a contract called game, and this is the contract where we are going to play the rock paper scissors game. So before I start this, let's just write out a few requirements, and we can just create that over here. So basically what we want to be able to achieve with this game is that only Alice and Bob can play, and Alice and Bob can play rock, paper, scissors. And they should be able to just play with their addresses, and once they both have played the move, any one of them or anyone can call an evaluate function, which will then decide who's the winner. So at this point, the first version of the game, we don't care about the actual privacy. So the only thing that we actually want in this game is that the Alice and Bob should be able to play the game, and that's all that matters at this point. So if you want to have a go, in my case, I am going to have two functions. So one function is going to be play. So play function is where a player can define what they are playing. So for this case, just to keep it simple, this game is only for two players, Alice and Bob, and In play, they just define what move they are playing. So rock, paper, or scissors. And we're going to have another function which is going to be called evaluate. And in evaluate, you essentially can say, given the two players who played this, so they are identified by their Ethereum address, evaluate who won. So it will return the address of the player who won. So if you want to have a go at it, you can pause the video now and have a go at it. Okay, so let's start by just writing the functional interfaces, just so we can see what is going on. So the first function we want is play. So play is a function and it's going to take in a choice. So in our case, I'm going to make the choice uint just to keep it simple. And since we know the number of moves are very low, there's only 3 moves, rock, paper, or scissors. We can make it uint 8 to save some storage. And we're just going to call it choice. And this function is going to be external because we are not going to call it internally. And you can write the function. Okay, so this is going to be a play function. Now we're also going to have an evaluate function. So in the evaluate function, we are going to take in 2 addresses. So the address of Alice and the address of Bob. And again, this function is also going to be external. And this function is also, since it's only doing like things that are not changing the state, it's only evaluating, we can make it view, which means that it's not changing the state of the contract. And after that, we can just make that, so it's going to return an address. So it's going to return an address, which is going to be something. So again, now that you have the interfaces of both of the functions, have a go at implementing this contract and see where you get to. So pause the video here and try to solve it. Okay, so just to give you a few more hints before we dive into the solution in the next video, you have seen that I am using uint 8 here. This is basically how I have chosen to store the choice, and in the next iterations we will change that to something else. But just to get it started, this is very simple to do because numbers are very easy to compare, and you can think of like what kind of storage you can use. Anything is fine. For now, we just want to be able to play the game. And also you can see that I am mapping Alice and Bob as the addresses. And as an additional hint, you can use something called message to sender, which will tell you who called this contract. And you can use that in the play function. So in here, you can use message to sender to see what move they're playing. Of course, you can do validation and you can do a few other things, but have a go at it. And if you can't do it, in the next video, I will solve it with you line by line. Okay, so first of all, what we need to do is to be able to know what moves are. So we need to represent them in one way or another. So the thing that I'm going to go with is uint 8 for now. So let's just say we're going to say that rock is 0. And we're going to replicate that and say another uint 8 and rock. Well, paper comes next. So we can do paper equals 1, and we can do scissors. Okay, let's just keep it all capitals because it's gonna be consistent. So, okay. So now we have defined rock, paper, scissors. We can now know what moves are actually playable. So what we can do now is we can write a require function that choice must be equal to one of these things. So choice either equals rock or it equals paper or it equals, as you guessed it, scissors. Okay, so now we've basically said that choice must be equal to one of the three things. So let's see what it's complaining about. It is saying that, okay, well, I missed the equal, so that's okay. So this is the benefit of auto compile. It's compiling always, so as soon as you make a mistake, it can tell you that you made a mistake and you can fix it immediately. So now that we have already checked that, the player move is valid, we can now also check that they haven't already played a move. So what we want to prevent is that they haven't played a move. Well, but to do that, we need to actually know and have a storage mechanism for it. So the fastest or the fastest storage or the most efficient storage we have in Solidity is a mapping. So we're going to be using a mapping, and what we're going to be doing is we're going to do a mapping between an address and a choice, and the choice in our case is a unit 8. Of course, you can represent it in many different ways, and there's a lot of valid ways to do it. This is just one of them I've gone with. Of course, you can use structs, you can use something else, and feel free to do that. There is no obligation to use this. And you can also send me all of your solutions, and we can create a repo for that. So everyone can learn from it. And of course, I'm just going to make it public. What this does is that it will create a function for us so we can access, given a key, we can access the value. And for this case, we are just going to be calling it choices. So this is the simple thing. Now, the other thing we want to check is that the player hasn't already made a choice, so they're not, like, after they've seen someone else's choice, they're not reverting to anything. So we don't want people to do that. Therefore, we are going to say, okay, choices, and the choices of the message sender, which is what I was talking about before, should be equal to address 0. Now, the reason for address 0 is because address 0 is the default of. Oh, sorry, my bad. It shouldn't be address 0. It should be just 0. Because 0 is the default for anyone. So you can do that. And this basically means that they haven't already played a move. For us to keep it a little bit more simpler, what we can do is we can now change this to match that, and to basically say that it's 1, 2, and 3, because we know that 0 is where they haven't played a move, and technically we shouldn't be comparing a non-played move to a played move. So just to make sure of that, we are now allowing this. And because we are just comparing variables, it's completely fine to just change the variables and not have to worry about the other statements. So, I mean, of course, we can represent the 0 as an unplayed move as well, or a player hasn't played. So once we have that, we can now do choices, and now we can just set what they are playing. So we've done all the verification that we have to, and now we can say, okay, well, they're playing a valid move. We know that they haven't played a move before, so we can just do this. And this is all that there is to it for the play function. So now if you want to have a go at the evaluate function and see if you can get it to work, go for it and pause the video here And if you can't, then I'll go through the solution with you. Okay, so we can now do the evaluate function. And the first thing that we can do in the evaluate function is basically see that if they have played the same move or not. So for this is actually very simple. What we can do is we can do choices of Alice. So if the choices of Alice equals the choices of Bob, then we know that's actually a draw. So if it's a draw, then we are just going to say return address 0. So we're gonna say the address 0 is if it's a draw. If it's a draw, we don't have to do any computation at all, and it's perfectly fine. But if it's not a draw, then we have to check. And for this, I'm not going to use any smart ways. I'm just going to write if statements. You can do things better, but this is just to keep it simple. And just, because that's not the aim of this. So we are just going to be writing simple if statements to check who won. So we are going to say if choices Alice. Okay, so if choices Alice equals rock, and so again we're going to do an and we're going to do choices Bob equals paper, then we know that Bob has won because paper beats rock. So we're just going to say return Bob. Of course, these are just the addresses that we are getting, and we're just comparing. So given this, this is going to be whatever choice they made. And if their choice is rock, if Alice played rock and Bob played paper, then Bob won, and then we can do a lot of else ifs. So again, you don't have to watch me do that. You can try to write it yourself and see how you go. And only if you get stuck, you can come and see the actual result. So I'm going to finish up writing all of these, and we'll see you in the next lesson and talk about the solution a bit more. Okay, so let's go through this a bit more. So we have if Alice played rock and Bob played paper, then Bob won. If Bob played rock and Alice played paper, then Alice won. If Alice played scissors and Bob played paper, then Alice won. And if Bob played scissors and Alice played paper, then Bob won. If Alice played rock and Bob played scissors, then Alice won. And if Bob played rock and Alice played scissors, then Bob won. So these are just just the rules of the game. It's the same with like if you're implementing tic-tac-toe or if you're implementing any of those. And this is essentially a basic version of the game we have. It's not perfect. We know that. You can write it much better. You can do a lot of fancy stuff. You can probably even do it in a single line. But just to keep it simple, we have it this way. And so now I want you to think about what are the most common problems with this approach. So now we can go and of course deploy this contract. So we can compile it. It's already on auto compile, and of course we can deploy it. So when you deploy the game, you can you can do different things, and you can of course check that indeed it will work. So you can play. So this guy with the address ending at C4 is playing a move that is, let's say, rock. And you can play the move, and it successfully registers it. And now I'm going to use the second address. So now you can see it's B2 instead of C4. And that's going to play, let's say, scissors. So it's rock versus scissors, which means that scissors should win. Now, of course, we can check the choices here with the address. And what we're going to say is, let's see who wins. So again, I'm going to copy the address from here. And the address, I'm just going to paste it, put a comma, and I'm going to copy the second address. And again, paste it after that once I've finished. And let's see, evaluate. So it says that the address with C4 has won. And let's look at the choice of C4. So this is the C4, and C4 made a choice which was 1. So rock, paper, scissors, which is what we expect. So the game is working onto a very basic level, and I want you to write down all the problems that you think of this. Play around with it. If you have anyone, give them an address and play around with them and see what it is. And we'll talk about all the problems with this approach in the next lesson. Okay, so now that we have a version of the game, we can look at what are the drawbacks of this. And you would have correctly guessed or thought about that. The biggest problem with this is that once a player has played the move, the last player or the second player always gets the advantage because they can see what the first player played and then they can respond accordingly. So the second player will always win regardless of whatever the move the first player will play because they will know what they're playing against. And this is because their values are directly just 1, 2, and 3. So this is one of the problems that one of the assumption of this is that they all are playing simultaneously, which is not a very real assumption. So we have to do something to avoid that, and to basically say that the first player should not be able to tell the move of the second player, and sorry, the second player should not be able to tell the move of the first player. And we will look at how to do this in the next lesson, but I want you to also see what other improvements we can make. So we'll look at how we can improve this further and basically not give that advantage to something, and we'll improve upon this in an iterative fashion. So let's see how we can do that. Okay, so let's think about a solution. So the reason that they can now see what their moves are is because they can say that's just 1, 2, 3. Well, we can make it slightly complicated and see if that helps. So, for example, what we can do is instead of using a uint 8, we can now use bytes 32. So, of course, bytes 32 is, just hexadecimal. And what we can do is we can hash something. So we can use kekek256, which is a hash function. And we're going to talk a lot more about all of these cryptographic primitives in the next modules, how they work, what their advantages and disadvantages are, where to use them, and why one of them is good ideas and where not to use them. But let's just do this for now. So abi.encode path, because we are going to be using a string. So, and we can now do, for example, that this is rock. So we can do the same thing for everything else. So I'm just going to copy this across just because I'm lazy and I don't want to type. So we can now do this. Of course, they're not all rock. Some of them are papers, and some of them are scissors. And of course, it's going to complain because the types are wrong. So what we want to do is actually make it bytes 32. And bytes 32 is actually a great type that Solidity supports. And the hash of that is always going to be that. So the hash of any string is always bytes 32. and this is why there is the hash collision problems that you see. And now it's going to complain that you are trying to compare a bytes 32 choice to a unit 8 choice, which is not what you should be doing. So we are going to change that and say that now people have to play bytes 32 choice, or actually what we can do is we can allow them to play a string choice, and so they can say, well, they're playing that. But again, if we allow string, then it's just open. So what we are going to say is that people are going to be now playing in bytes 32 choices. And if they're going to be playing in byte 32 choice, then we also have to update the mapping to match that. So that's going to be byte 32 as well. And now it stopped complaining. So everything is now fine and we don't have to do anything. So what we can do now is we can delete the contract which was deployed before, and again we're going to use two addresses, and you can now do this to make it so now people have to know what this means. So they have to know. So now anyone who's playing has to know what the rock, paper, and scissors are, and they have to play. And you're not just simply 1, 2, and 3. But as you may have already noticed, there is a big problem lying around somewhere. See if you can spot it, and I'll talk about it more in the next video. So as you might have figured out already that just by doing a hash of rock, it is not much different to just saying 1, 2, or 3. Yes, we've done some obfuscation as there is no 1, 2, 3 anymore, but if you actually see what's actually stored here, if I just make it public, just so we get a function where we can see the results, we should be able to see that they are actually always the same. So once you know that rock evaluates to a certain hexadecimal, you can still do the exact same attack as before. And this is often a mistake that a lot of people make, where they think that just by hashing something it's secure. It's not, because once you know that rock is this, paper is this, and scissors is this, it's no different to anything else, because you can call it a lot of times and it's always going to be this hash. It's not going to change. It's a one-way function which takes a string and then gives you a result, and that's going to be always the same. So if I'm playing paper and everyone can see that I've played paper, and then they can beat me with scissors always, and it's the same thing. So we have not actually improved whatsoever. And now you might be thinking, well, we really did a lot by adding a hash function, and it's much more complicated than before, so why doesn't this get the job done? Well, in these systems we have a lot of tools like hash functions, but if you don't use them correctly, then they don't really work. So in this case, we've used a hash function, but it's really given us no privacy at all. Now, can you think of a way by using the existing setup that we can actually make it so that this becomes irrelevant? So when players play a move, they can play any of these three moves, but it's not possible to see until the evaluation point that what move they've played. So we're gonna have to make quite a few changes, of course, but I want you to see how you could fix this problem by yourself, and I'll talk about the solution in the next video. Okay, so now this is where it gets very interesting, where we actually find out how to do this in a way which is more consistent. So what is the problem? Well, the problem is that this rock, paper, scissors, no matter what you do, are always going to be the same. So what we need to do is introduce a source of randomness, which only the player knows and no one else finds out until the evaluation function is called. So we can now make things a little bit simpler. Well, we can now just say that it's just gonna be rock, and we can do this by using a public constant. And so now we are just removing the hash function from here, and you can kind of guess where I'm going to go with this. So the idea is every player, when they make a choice, it's a bytes 32, but we're not saying what's in the bytes 32 just yet. What's going to be inside the bytes 32 choice is, of course, going to be one of these, so rock, paper, or scissors, but it's also going to have a random source. So this bytes 32 is completely random. Like, only the player who's played the move knows what random thing they chose. And they can pick anything random, and bytes 32 will be entirely random. And we'll define how to do this. So basically, I'm just going to update the rest in the same way. So we have paper, and of course we're going to make it constant. I'm making it constant so it doesn't actually take up any more space, and it's actually stored in the bytecode of the contract. So these are just replaced with the actual values where they're used instead of them taking up a storage. So I can just copy this thing across, and I'm gonna make this again constant, and we can now replace this entire thing with just scissors. And of course I need to put that in in double quotes. So now we're not doing hashing here, we're not really changing anything here, but we have to do something. So we can't really say that the choice has to match one of the three, because the choice could be anything, and we're not going to find out what that is until a later point in time. The other thing is, because now we are checking for bytes 32, we should be checking with slightly more types. So we can just say that it's equals that. So they've not played a move before, and we allow them to play with any move now. Of course, if they play a move that we can't recognize, they fail anyway. So now this whole thing is great, but we're going to have to change the interface slightly. So address of Alice is fine and address of Bob is fine, but we need a few other parameters. So what we need is a bytes 32, which is going to be Alice's choice, so the actual choice they made, which is going to be comparable to the ones that we have above, stored in bytes 32. And also the second thing that we need, which is very important, is the randomness. So this is the randomness that Alice chose. So again, the same thing. We have the address book for Bob, and we need the bytes 32 choice for Bob. So what choice they made, and we also need the bytes 32 randomness. And we're going to see in a second on how we use this randomness. So again, Bob has some randomness and Alice has some randomness. And now we must verify that these randomness match up. So we are going to have a require, and in that require, we are going to check that what they claim is what they committed to. So this is where it actually becomes a commitment. And for this, we have to do some hashing. So what we are going to say is that the KEKEK256 hash of the Alice choice and So to do basically two arguments, you have to do API encode fact. Well, you can do API encode as well, just using fact. So you can do API encode fact, and you would have to pass in the Alice choice and the Alice randomness, and that should be equal to. So now we are going to compare this and say that it should be equal to what they committed to. So they have committed to say Alice, right? And this should match up. Now, if this doesn't match up, the problem is that they are not doing things right. So the reason that this choice is now not able to determine what's inside is because the two things are hashed together. So the Alice choice is essentially just rock, paper, or scissors, but there is some randomness. And that randomness makes the hash actually, just by looking at it, now you can't just say, oh, they must have played rock or they must have played scissors. Of course, if they pick not very good randomness, just like they always pick zero, and you do a brute force attack, then you can find out. So the randomness that someone picks must be completely random. And if it's not random, then you can break it. So the same thing we're going to do with Bob. So just to make sure that they have not, they're not trying to cheat the system, and they are using the right thing. So again, we can do Bob choice and Bob randomness. So we are going to say that it's Bob, and Bob actually committed to the things that they are saying that they committed to. So once these checks are done, now we know that whatever they committed to is what they are playing. So no one's trying to say that they played rock and now they're changing their mind, so they can't do that. And we've verified that because we've verified that the hash of the choice and the randomness is actually equal to this, which means if they try to change their choice, this would not match up. So the hash function has this property that if you hash two things together, and the order also matters, and if you do that, then it will match up. If you change the ordering, you change capital letters, you change anything, this will fail. So this will protect us for these things. Now we have to also see again the same thing. So we can now just see, well, we can't do this anymore. So the choices, we cannot use them anymore. Why? Because the choices have this randomness inside, and we can't really compare with randomness. So now that we've actually verified that Alice choice and Bob choice are correct, we can just replace wherever there is like choices Alice to replace it with Alice choice. And wherever there's choices with Bob, you can now replace it with Bob choice. And it's as simple as that. And now, although we're not looking in the mapping, we are confirming that it actually works because we reconstructed the hash from its original arguments, and we matched it against the one that was played with. And this is just to demonstrate that how important like randomness is. And we didn't do any fancy cryptography. We're still using just hash functions. All we've done is just added some randomness, and just by adding the randomness, we've changed everything, and we've changed the entire privacy model. And this is what this is the main aim of this module, to show you that just by thinking slightly different and trying to break the system, you can improve it. And maybe there's some things that I've missed out here, and I would love to be pointed out and shown how to improve this further. So go ahead and update your code to match this, and also see if you can find anything else. And This is now in a way where it's completely private. Two players can play this game. Of course, you can add more things in there, such as you can add that they get some money now, and but the main point is that now it's completely private after this. So when two players play, one player cannot say, oh, you've played this, so I'm going to play that. They both have to commit to something, and then it reveals in the evaluation phase. So Alice only has to reveal it. In general sense, this assumes, because we only have one function, this assumes that both of them are in the same place, or they've shared. I mean, the thing is that they can actually share this information, because once it's committed, it no longer matters. You can now reveal it freely because they can't steal anything, because it's already committed in the Alice choice and Bob choice. The problem would be that if they're actually able to update this later on, which they can't do because of the check we have, which essentially ensures that one player can only play once. Of course, you can add more functions such as reset and expand this further. And go for that, and you'll find the full code down below. Okay, so now I've updated it so that we have now replaced the choices Alice to Alice choice and choices Bob to Bob choice, and everything else remains the same. And as I've mentioned previously, this is the level that we want to get to, where we essentially assume that Alice and Bob will pick random choices. And of course, when you build the application on top of this, you can ensure that the randomness is actually automatically generated, and you can ensure that it comes from a good source, and it's not easily knowable. Because imagine if they're playing for $1 million each, or a million ETH each, then it's very, like, every player has an incentive to actually find out what the randomness is and play a move which will eliminate this. You can expand upon this further. As I've said, you can add more functions. You can add time. So you can add that you can, once a move has been played, the second move has to be played within a few hours or something. And you can, of course, expand this much further. But this is enough to demonstrate that just by using hash functions, it is not enough. You also need, in terms of a public blockchain, you also need to add randomness to make sure that just by looking at the choice itself, it does not reveal the actual choice. But at the same time, you also have to make sure that the commitment holds. If the commitment does not hold, then it's not very useful at all, because they can play anything. But if the commitment holds, then everything's fine. If the commitment doesn't hold, then we're in trouble. But I hope you've learned a lot in this. And if you think that there should be other things in there, feel free to message me, or email me, or just leave a comment in the course, and I'll pick it up. And that's all for this, and we're gonna do a wrap up now. Okay, so welcome to the end of module 2, and congratulations on playing rock, paper, scissors on the public blockchain, and having to implement that in Solidity. So let's take a look at what we've learned so far. So we've implemented rock, paper, scissors in Solidity. We've played it in our browser. Of course, you can deploy it to a testnet and deploy it onto the public blockchain and play it for real Ethereum and improve the code as much as you like. What we've learned is using hash functions firsthand. So you now have an idea of how to use hash functions, what they mean, how the arguments are important. So you can play around with hash functions more and see the changes that are made. And what we also learned is that using hash functions alone is not enough. It's an obfuscation, but it breaks down very easily and is not enough to guarantee privacy. And this is why We need to understand privacy in public blockchains and the fact that everyone can see what anyone is doing. And because they can see what they're doing, it must be hidden. And the public verifiability is very, very important because the smart contract can verify alone without needing a third party. It does not need an oracle to tell it, it doesn't need anyone to tell it anything, and it can verify it. And in your applications, if you can do that, always, always, always do that. Do not rely on oracle, do not have any more trust assumptions that you need. And in a lot of cases, you are going to use randomness. And true randomness is very, very hard to achieve. And the best we've found so far is probably just asking random people, X amount of random people for X randomness, and hoping that at least one of them will do it properly or honestly, such that the whole system will be entirely random. So you can read about it more. It's a big topic of randomness in cryptography and in cryptocurrency as well. And we learn how to use that in our applications. We also learned the attack vectors of a specific application, such as rock, paper, scissors. And this is very important because every application that you develop has different attack vectors and different attack models and different threat models. So the privacy depends on the application that you're building, but the assumptions should always be the same, that everyone can see the public blockchain, everyone is able to see this, and what happens if people find out certain information that they should not. So in our case, if the player could see at the start that the first player was playing rock and the other was playing scissors, so the second player always had the advantage and they could always beat the first player. So these are some of the things that we've learned, and in the next modules we are going to deep dive into more sophisticated topics. We are going to be looking at commitment schemes, Merkle trees, ring signatures, and many, many more, like zero knowledge proofs. And we are also going to do some amazing projects like this one. If you have a project that you would like, you can also suggest this, and we will try to do that as well. So that's all I have for you now, and I hope you've enjoyed implementing rock, paper, scissors and playing with it.